15.6 notes. Directional derivatives and the gradient vector. This is just a quicker version of introducing gradient vector, so we won't get through all the notes, but we will introduce the gradient function vector today. Let's do the warm-up. Let's review finding partial derivatives. So partial derivative with respect to x of y is 3x squared minus 3y. The partial with respect to y of xy is negative 3x plus 8y. Now the partial with respect to x at a coordinate point 2, 1 would be 3 times 2 squared minus 3 times 1. So that would be 12 minus 3, which is 9. And the partial with respect to y of 2, 1 is negative 3 times 2 plus 8 times 1. So that's negative 6 plus 2 is, negative 6 plus 8 is 2. We are going to find out the answer to this extension question in these notes. If you are at the point 2, 1 and have rotated 45 degrees counterclockwise from the positive x-axis, what's the slope? Right now, we only know partial derivative, so partial with respect to x or partial with respect to y. What's the slope when you're looking at the x-axis, when you're looking at the y-axis? But what if you're looking at a different direction? How do you find the derivative? The directional derivative will answer that question. So because these are quicker notes, we won't look at the formal definition of derivative using the limit. We're just going to go through the quicker definition. So we want to find the rate of change or the derivative of our function in the direction of an arbitrary unit vector, and not necessarily just like with respect to the x-axis or the y-axis. So the derivative, the directional derivative without using the limit notation is the partial with respect to x times a plus the partial with respect to y times b. Now, a and b are parts of the unit vector. If you are given, not the unit vector, but you're given the angle with respect to the positive x-axis, then you can write this definition of the directional derivative in a different way. The a comma b is replaced by cosine theta comma sine theta, because remember, the unit vector will give us that cosine theta comma sine theta as a unit vector. So let's go ahead and use these definitions. So let's go back to our warm-up and we can answer this question now. So let's go ahead and write in the definition of directional derivative of our function. That is the partial with respect to x of xy times cosine of theta plus the partial with respect to y of xy times sine of theta. And we are going to find the directional derivative at that point 2, 1. So we already know that the partial at 2, 1 is 9, so we'll replace that pretty soon. And the theta is pi over 4 because that is the angle, 45 degrees. And we will find the partial with respect to y of our x, y is 2, 1 times sine of pi over 4. So we will replace the 9 with our partial derivative with respect to 2, 1, and we'll replace the partial with respect to y with the 2. So let's go ahead and rewrite all of this. And also let's review if we want to find cosine or sine of pi over 4. Let's say this is pi over 4. That coordinate point is square root of 2 over 2, comma square root of 2 over 2, which is our cosine, comma sine. So our directional derivative at the point 2, 1 is 9 times the square root of 2 over 2 plus 2 times the square root of 2 over 2 So we have 9 square root of 2 plus 11 square root of plus 2 square root of 2 all over 2. So that's 11 square root of 2 over 2. What this tells us is that if you are at the point 2 comma 1, and if you replaced 2 with x and y with 1, you would, in that original function, you would get z is 6. So we're on this curve at the point 2 comma 1 comma 6, and if I'm rotating and looking at 45 degrees counterclockwise, we would be then, the slope would be going upwards at a slope of 11 square root of 2 over 2. So that is what the directional derivative tells us, that we would be walking upwards. Okay, so that's directional derivative at a degree. So let's go ahead and let's now go and do another example of directional derivative with a vector. So let's go ahead and use the other formula for directional derivative. And so we have, let me write that down, and we have the directional derivative of f of x comma y is the partial with respect to x times a plus the partial with respect to y of x comma y times b. And remember that that a and b are the parts of the vector, of the unit vector. So let us review. If we are given this v value, then the unit vector can be written as the v vector divided by its, oh, I'm not sure how I got up there, divided by its length. So that would be 2 comma 5 divided by the length is the square root of 2 squared plus 5 squared. So this is 2 comma 5 divided by square root of 29. So our A component is 2 over the square root of 29. Our B component is 5 over the square root of 29. That is our unit vector. So let's go ahead and now write down more information here. So our directional derivative of our function at the point 2 comma, oh, before doing that, let's just do x comma y, because we have to figure out what that partial derivative is. With respect to x, that is 2x y cubed, and then that would be times that a, which we know is 2 over the square root of 29, and then plus that partial with respect to y is 3x squared y squared minus 4, and that's times b, which is 5 over the square root of 29. Now we'll plug in our particular number. So we have the partial with respect to the directional derivative is at the point 2 comma negative 1 is 2 times negative 1 cubed times 2 over the square root of 29, and then plus 3 times 2 squared times negative 1 squared minus 4 times 5 over the square root of 29. And let's keep going here. So the directional derivative of our function at the point 2 comma negative 1 is a negative 4 times that 2 over the square root of 29 plus, I'm not sure why this isn't writing well, 3 times 4 is 12 minus 4 is 8, and then times 5 over the square root of 29. And so our answer here is the directional derivative at our point 2 negative 1 is negative 8 over the square root of 29 plus 40 over the square root of 29 which is 32 over the square root of 29. Again, that tells us at the coordinate point of x comma y 2, -1 in the direction of the vector 2, 5, this slope is a positive 32 squared over the square root of 29. We are pretty good with directional derivatives given a vector or a theta. Now let's talk about gradient. So let's go back up to our information that we know. We know that the directional derivative is a partial with respect to x times a plus a partial derivative with respect to y times b. We also know from way back the dot product tells us that if I take two parts, so let's say our partial with respect to x and the partial with respect to a, I could write that as two vectors, and those are our x coordinates of the vectors, and then our partial with respect to y times b could be written as the y values of our vectors. So the directional derivative can actually be written as a dot product. We've seen it right here. So directional derivative of our function f can be written as this f partial derivative of x comma partial derivative with respect to y, and then dot the unit vector. We will be using this notation often, and in fact, we're going to use this part a lot, partial comma partial, as the vector. We're going to use it so much that we're going to now call that the gradient. That's the gradient of f, or you can show it as an upside down delta, or we can call it a del f, or you can call it a nabla f. So gradient, this is the formal definition of gradient, is your partial f with respect to x, comma partial f with respect to y. Very important. We can also, as we talked about before, that the directional derivative can also be written as that gradient time dot the unit vector. So now let's go back to this last problem, and instead of doing it using this older method, we could actually do it by using the dot product. Let's see this. So if we do it using the dot product, let me just do this in red now. That means that the directional derivative of f is the gradient of f dot the unit vector. So I could now plug in that coordinate point 2 comma -1. The gradient is, oh yeah, that was -4 comma 8. So -4 comma 8. The gradient is a vector dot the unit vector, and that was in this problem 2 divided by the square root of 29 comma 5 over the square root of 29. And a dot product, you multiply the x values, so -4 times 2 over the square root of 29, add, multiply the y values, and we get the same end result of 32 over the square root of 29. So the directional derivative is a scalar. It is a number. It tells us the derivative at a particular point. And the gradient is a vector valued function. We will find out later that the gradient will help us determine the steepest part of a curve. Let me just give you kind of a preview to that idea. So let me just scroll down a little more. So let me just change this color to blue. So we know that the directional derivative of our function is the gradient of f of x comma y dot product of the unit vector. So that is a dot product. And from way back in our class, we found out that the dot product, like a, ooh, this is not writing anymore. Let me get another pen that'll write. We found out that a dot b, a dot b is the length of vector A times the length of vector B times the cosine of theta, where theta is the angle between your two vectors. Since the gradient is a vector and u is the vector, we also know that that equals the length of vector of those two vectors. So the length of the gradient and times the length of the unit vector, which is just 1, and then times cosine of theta. So this is the directional derivative. So if you want the directional derivative to be the biggest value, then that means that, well, the unit vector is just 1. That means that cosine has to equal the biggest it can, which is 1, and that occurs at 0. So that means that the direction of the gradient and the direction of the unit vector, when they equal each other, you will have the biggest directional derivative. And then there are a lot of applications to this. So let's say you're on a surface and at a particular point, and you want to go in the direction of the greatest ascent. Well, you would go in the direction of the gradient. So lots of fun stuff coming up. We'll talk about how in the plane, gradients are normal to the level curves, and in space, gradients are normal to level surfaces. But for now, we just know the basic mechanics of finding the directional derivative and knowing that the gradient is a vector. It is the vector of the partial derivative with respect to x, comma, partial derivative with respect to y. Hope you learned something today and hope you had a good time, and looking forward to teaching more later. Bye-bye.